Okay, why real numbers are superior to rational numbers? That's a pretty good way to describe what the arc is. And so what we finished up with last time was this a couple of concepts: least upper bounds, greatest lower bounds. Right. So you have a set. You have a set that lies within an ordered set, right? And you have something called a least. You have something called an upper bound, right? And you have these things called. You have something called a least upper bound, right? So the least upper bound is something that is less than or equal to every other upper bound. Okay, so it's the least of the upper bounds, right? In this, and conversely, you have this notion of a greatest lower bound, right? You have a set; it has a lower bound. You have a set. You know, it may have some lower bounds, and you have this thing called the greatest lower bound. It's a lower bound, and it's bigger than or equal to all other lower bounds. Okay, so we have these two things, two ideas: least upper bound and greatest lower bound. And what we finished up with was the fact we had introduced, we had done an example where we saw that Q, if we consider the set, so recall, we let this set A be the numbers in the rational numbers that were positive, and square was less than 2, right? And basically where we finished up was we observed that, in fact, this set A has upper bounds, but in fact there is no least upper bound. There is no least upper bound. Okay, and the way you see that is by looking at the set which Rudin calls B. You look at this set, you know, the other positive numbers, right? The other positive rationals, the guys whose square is greater than 2. And we saw that there's nobody whose square is equal to 2. Okay, so you look at you've got this set, and you look at all the other numbers, and this turns out to be these guys are all upper bounds of A, but there is no smallest one. There is no least one. Okay. So and we didn't show that, but the proof of that goes along the same lines as the proof that we used to show that there's no biggest one here. Right? If you read the text, and I assume you all did read the text, you see that exactly the same construction goes to show that where you see that whenever you have somebody here, there's somebody in the set who's bigger. The same thing goes if you have somebody here, you can find somebody in the set who's smaller. Okay, and so this set has no least. There are upper bounds, but there's no least upper bound. Okay, okay. So and we sort of rushed it at the end, but there's this thing called the least upper bound property, and let me write it down properly. Definition. Say S is an ordered set. If for any subset of S, so any non-empty subset of S that has an upper bound, there is a least upper bound in S. Okay. Then we say S has the least upper bound property. The least upper bound property. Okay, so if you have a set, if you have an ordered set, and it has this property that whenever you have a set with an upper bound, there's going to be a least upper bound in the ambient set S. Then that ambient set S, we say, has the least upper bound property. Okay, and what we just noticed is that Q does not satisfy the least upper bound property, right? Because we have this set here, it has upper bounds, but there is no rational least upper bound, right? Okay, there is no rational least upper bound, and so Q doesn't satisfy the least upper bound property, as we've stated in here. Okay, so this is actually going to be maybe the key thing that distinguishes R from Q. Okay, that R, although we're not going to construct it, if you construct it properly, then it satisfies the least upper bound property. Okay. Okay. So any questions about this? It's a little bit abstract, but hope it's all right. Okay. Any questions? Okay. Just to make a joke or something. I think I'm actually not suited to be a teacher, in the sense that I think a teacher should be very cheerful and encouraging, right? And my natural instinct is not to be cheerful and encouraging. Like over the summer, I sort of revert back to my normal form, which is like, like this, right? Sort of expressionless. And at the beginning of each year, I have to sort of revive these abnormal instincts of teacherdom, right? And start start smiling. Right? Okay, so it'll happen eventually, but right now I'm still in my normal state. Okay. Okay, so we're going to start off with so the least upper bound property. Okay. And my father once told me, he said, "Why don't you wear glasses at the beginning of the year?" I'm not sure what this means, but he felt that I looked more friendly with glasses. Okay. Okay, so least upper bound property, and you can probably guess what we mean when we say if I say greatest lower bound property, then you can guess what that means, right? It would mean that your ambient set has the property that whenever a set has a lower bound, then there exists the greatest lower bound. Okay. Why don't we care about the greatest lower bound property? Because it's the same thing as the least upper bound property. Any set that has the least upper bound property is going to have the greatest lower bound property, and vice versa. Okay, but let's see that. Okay, so S an ordered set. S has the least upper bound property. Implies that S has the greatest lower bound property. Okay, so let's think about the proof. Suppose S has the least upper bound property, and say that what are we calling it? B. B is a subset of S. It's not equal. It's a non-empty subset of S, and is bounded below. Suppose you have some set that's bounded below, and we want to see that it'll have a greatest lower bound. So suppose it has a lower bound, we want to see that it has a greatest lower bound. Okay. Okay. Can anybody tell me the strategy? Can anyone tell me the strategy? Does anyone remember from reading the book what the sort of line of the proof is? How do we want we want to find the greatest lower bound, right? We want to find the greatest lower bound. We know that the set has the least upper bound property, right? How do we use the least upper bound property to get a greatest lower bound? So think for 10 seconds, or think for a minute. Don't say anything, don't blurt it out. Okay, talk to somebody nearby and say, this is how you do it. If you remember, or if you don't remember, make up something. Say, this is how I think you do it.
Another set where the opposite bound. So whatever is bounded below by is the subset that's bounded above by that. Do you know what I mean?
Yes.
So then knowing that you have the lowest upper bound property, right, and then you find that
Okay.
so then you know that you have the answer. I think that's what we're doing. Yeah. I can't remember what it is.
I'm not
It
sure.
was like a really short. It was like a line.
Okay, so does anyone remember what you need to do, or can anyone make up what you think we need to do? Right, we're trying to find, we're trying to show that this set has a greatest lower bound. A greatest lower bound. We know that any set with an upper bound has a least upper bound, right? Well, you can guess that this greatest lower bound is going to be the least upper bound of some set, right? What set?
We'll call it the lower bound.
The set of lower bounds,
Yeah.
right? It will be the least upper bound of the set of lower bounds. That will make it the greatest lower bound, right? We have only one tool, right? We have only one tool at this point. We better use it, right? So you say, well, we're looking for the greatest of the lower bounds. So let's look at all the lower bounds. Consider the set of all the lower bounds. So let L be the set of all lower bounds of B. Okay. So we know that the set L is non-empty, right? Because we said that B is bounded below, right? So B has one lower bound, so we know that L has at least that element, right? And right, to use the least upper bound property, the set has to be non-empty and the set has to have an upper bound. Well, does L have an upper bound? Sure. What's an upper bound of L? Tell me what gives us what lets us know that there is an upper bound to this set of all lower bounds? As long as you keep your sanity, it's fine. Yes.
Because L is in S, and S has the least upper bound property.
No, I mean, so that doesn't give us that L has an upper bound, right? We need to use that least upper bound property, we need to show that L has an upper bound, and then we can invoke the least upper bound property. Dave?
Because L contains all the lower bounds of B, and B is containing S, and S is bounded up. It has a lot of upper bounds, so basically
Not quite. You can tell by my shoulders that it's not quite working, but you're almost there. So many people. Why are you all in here? John?
Is it just simply because
Yes.
B is
That's the way
bounded below, so then L is bounded above by B?
Yeah, basically, right? So, right, I mean, the phrasing is a little bit, basically, yeah, right? L is all the lower bounds in B, right? So just choose anybody in B. That will be an upper bound for everybody in L, because they're all lower bounds of B, so anybody in B is bigger than them, right? Right, okay. So L is bounded above by any element of B, and remember B is not empty, so we do have an element of B to work with. Okay. 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 So okay. So we can use the least upper bound property, right? So least upper bound, since S has the least upper bound property, we know there exists a supremum of L. Let's call it there exists a supremum of L in S. Okay. Okay. So we're going to claim that that guy, supremum of L, is actually the greatest lower bound. It's the greatest lower bound of B. Right. Okay, that's the guy that we're hoping will solve our problem. Okay, so so part of it is easy. Being the greatest lower bound means that you're bigger than all the other lower bounds, right? But this is by definition the supremum of the set, right? So it's going to be bigger than or equal to all other elements, all elements of that set, right? So it's definitely going to be greater than all the other lower bounds. Okay. So let me say it this way: what do we have to show that this is the greatest lower bound? One, that it is a lower bound, and two, that it's the greatest of the lower bounds. Okay. So there's two parts to this. One, so we need to show one. We need to show one that supremum is bigger than or equal to all lower bounds of B. Any other lower bound of B. Okay, but it's the supremum, right? It's the least upper bound. It's an upper bound of these guys, so it's going to be bigger than them, right? So that's obvious. It's your supremum of L is the least upper bound of L, and remember L is all the lower bounds of B, which is all of L, the lower bounds of B. Right? So it's definitely bigger than all the lower bounds of B. Okay, so that part we don't have to worry about. That's easy. Okay. The part that's difficult, the part that needs a little bit of work is that so what we have to show then is that supremum of L actually is, so claim, supremum of L is a lower bound of B. Oh, yes.
So the greatest lower bound is equal to the least upper bound?
What we're trying to show is that the least upper bound of the set of lower bounds is the greatest lower bound. Okay. of the greatest lower bound of B. Okay. Okay. So let me just do this last part for you. Suppose that you have some number gamma that's less than the supremum of L. The supremum is the least upper bound of this, right? So in that case, gamma is not an upper bound of L, right? Because it's less than the least of the upper bounds. Are you okay? Read? Good. Hang in there. Okay. So now observe that, or recall that any element of B is an upper bound of L. Right? So the conclusion is that gamma is not in B. Okay? Right? Because if gamma is not an upper bound of L, anybody in B is an upper bound of L, so gamma can't be in B. Okay? Okay. So now let's look at the contrapositive of that. The contrapositive is to say that if gamma is in B, then gamma is greater than or equal to the supremum of L. Right? We started here. Suppose gamma is less than supremum of L. In that case, gamma is not an element of B. We contrapose that, right? If gamma is in B, then it must be greater than or equal to the supremum of L. In other words, so what does that tell you? The supremum of L is less than or equal to every element of B, and so, right, supremum of L actually is a lower bound of B. Okay, and we've already noted that it has to be the biggest, and so we found the biggest of the lower bounds of B. Yeah, Mia.
I'm a little bit confused about, maybe it's just the order we did it.
Okay.
But so in the statement for part one, we already said supremum of L is greater or equal to any other lower bound of B. So aren't we already kind of assuming that the supremum of L is in fact a lower bound of B?
No, just that it's bigger than all the lower bounds. Sorry, there, is that
Okay.
better?
Okay.
Yeah, the wording is bad, very bad. Yeah. We need to show that it's bigger than any lower bound and that it actually is a lower bound. Thank you.
Because it could have been, it could be just
It could be
the
something.
upper bound of L without being a part of L.
It could have been something that's bigger than all the lower bounds. So like suppose you have a set on the number line, and this is B, and here are all the lower bounds of B. Right, here are all the lower bounds of B. And maybe the supremum of L is something huge. It's bigger than all the lower bounds, but it's not a lower bound of B. Okay, but that doesn't happen, of course. But we needed to show that it didn't happen. Okay. Okay. Everyone all right? All right. Anybody confused? Anybody confused? Yes, E, go ahead. Yeah.
Oh,
Thanks.
If here, you said that L is belong to the B.
L belongs
No,
to
you said L is belong to B and B is belong to S, and
No, remember L is the set of lower bounds of B. B is in S. L is another set. It's a collection of lower bounds of B.
okay, all right.
right? L is the collection of lower bounds of B. And then we look at we use the least upper bound property to say, well, that set having an upper bound has to have a least upper bound. And then we see that that least upper bound is actually the greatest of the lower bounds of B. Okay. 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 So now we're going to introduce the notion of a field, because as you have read, what R is going to be a field, right? And that has this least upper bound property. So we have to explain what a field is. So okay. So a field is something that satisfies a set of axioms. Okay, so let F be a set possessing two binary operations denoted by plus and dot, right? Plus addition and multiplication. Such that these operations satisfy a whole bunch of laws. Okay, all of these laws are things that you're familiar with. Okay, so just for an example, for examples of fields, the rational numbers, the real numbers, the complex numbers, these are all fields. Okay. There are many other fields than these. They all will satisfy certain laws. Okay. So I don't think you want to copy these things down because it's all in your book and it's not that exciting. But let me just write them up. Okay. So the first is additive closure. So that is whenever you have two guys in the field, then when you apply this first binary operation to them, you still stay within the field. You don't leave the field. Okay. So two guys in the field, their sum is still going to be within the field. Number two, commutativity of addition. That whenever you have two guys in the field and you add them together, it doesn't matter what order you add them. Associativity. And if you add two guys and then add on the third guy, it's the same thing as if you add the latter two first. Add the first guy onto the sum of the latter two. Number four, the existence of an additive identity. There exists an element called 0 in F with the property that for all x in F, x plus 0 plus x equals x. Okay, so this is guy in your field, and whenever you add him to somebody, then nothing happens. Okay. And the last one, the existence of additive inverses. For each x in your field, there exists somebody called negative x in the field, such that when you add them together, you get that additive inverse guy, the additive identity guy that we mentioned before. Okay. One comment I want to make is that at this point we don't say anything about the uniqueness of 0 or this additive inverse, right? We say that there is a 0 element in there, but there could be, it seems to be acceptable to have more than one 0 element. Okay. Similarly, it seems like there's nothing here where we don't say anything about this thing being unique. There could be multiple additive inverses at this point. Okay. Seems like it. Okay. That's actually not going to. That's actually going to turn out to be false. But at this point, we haven't made any such constraint. It seems. Okay. And then there's a bunch of analogous axioms for multiplication. So closure for multiplication, right? Whenever you have two elements in your field, then x times y is also going to be in your field. And 2, commutativity. And 3, associativity. And 4, existence of a multiplicative identity. Right? There's somebody in your field. There exists a number called 1 in your field that is not equal to 0, not equal to the 0 guy, such that 1 times x equals x, right, for all x in F. Okay. And the last thing is for all x in F, F but not 0, there exists something called 1 over x in F, such that x times 1 over x equals the the multiplicative identity guy. Oh, and then, of course, there's one property that involves both of them. For all distributivity for all x, y, and z in F, x times y plus z equals xy plus xz. Okay, so these are, this is what a field satisfies, right? These are, if somebody says you have this thing and it's a field, you know that it satisfies these. This is what a field is. Okay. If we look at, say, the n by n matrices, is that a field? Is that a field? Are the n by n matrices a field? Well, let's see. If you add two matrices together, you still get a matrix the same size, an n by n matrix. You add them in opposite order, that's okay. You can do associative. There's an element. Is there an element 0? Yeah, the matrix consisting of all zeros, that would work. Additive inverse. Is there an additive inverse for every matrix? Sure, right? Okay. If you take two n by n matrices and you multiply them, then it's okay. Is it commutative? Two matrices, AB equals BA? No, false, right? False. Associativity, is that okay? That's okay, right? Associativity is okay for matrices. Multiplicative identity, yes, right? The identity matrix, 1, 1, 1, 1, 1 down the diagonals, right? Existence of multiplicative inverses? No, right? Not necessarily, right? Right? This would say that for any non-zero matrix, you'd have to have a multiplicative inverse, but that's not true. Distributed property, that's okay. Right? So it's not a field. Right? It's not a field. Okay. So this is what a field is. There's a bunch of other properties that follow immediately from the axioms. We don't include them in the axioms because they just follow. They're just consequences of the axioms. So consequences of field axioms. Okay. Is a proposition. So there'll be 4 parts to this. First, x plus y equals x plus z implies that y equals z. X plus y equals x implies that y equals 0. Number 3, x plus y equals 0 implies y equals negative x d. Negative x has to equal x. Okay, so these are all things which you would sort of expect to be true in your fields, right? It's certainly true in the fields that we know. It's also true for every field. It's not the most exciting thing, but we do have to prove it. Okay, so so maybe I'll let you try. Take 2 minutes and see if you can prove, at least the first one. And once you get the first one, basically everything else follows. Okay, so take 2 minutes and see how many of them you can get from just proved by using the axioms. Okay, use the axioms to prove these statements. Okay, it's not exciting, I have to say. We'll do it, and then we'll never do it again, I hope. Okay, turn to somebody nearby and tell them how to do the first one. Jonah, you have talk to these guys. Me and that. Talk to Jonah.
Oh yeah, sorry.
It's okay.
He's by himself. He's lonely.
In our circle. So we were just talking about A. We were saying we use A5 to add negative x to both sides. And then you get like 0 plus y equals 0 plus z. And you use A4 to divide y equals z.
Yeah, I did very similar.
Everyone. And then once you have I just redid it every time.
X plus 0 around the x.
Okay, so how do you do the first one? Right, suppose you know that x plus y equals x plus z. Then you just, what do? Can somebody? You add negative x to both sides, right? So you got this plus x plus y equals x negative x plus x plus z, right? And then, if you want to be really tedious about it, you say, well, we can associate these guys, right? Right, by property A3, we can associate these guys right, and then we use property A5 to say that this is 0, then we use property A4. Yes, property A4. 0 plus anything is itself, and we end up with y equals z. Okay, right. So axiomatic reasoning. Okay, right. So, right. So whenever you have something that satisfies these things, you know, and actually we use only the things on the left, it has to have, it will satisfy a cancellation. Okay. Okay, and so what about the second one? Second one, basically do the same thing, right? You just add negative x to both sides again. You get up with 0 on the right, get y equals to 0, right? What about this one? Same thing again, add negative x to both sides, you get y equals to negative x, right? What about this one? To show that negative x equals x. Maybe you could use e.
I think negative x equal to negative x.
Negative x equals negative x? Okay. Negative x equals negative x.
Then move the negative x. Move the negative sign to the left sign.
How do you move the negative 1 to the other side? Yeah, it's not so. It's maybe easier to use this. Let's use this one. You say, well, look, if x plus y equals 0, then y has to be negative x. So you say, well, look, negative x plus negative x is equal to 0. Oops, let me write it the other way. Negative x plus x is equal to 0. And so x must be, this guy must be negative x. Right? Okay. So using C, you can get D. Okay. Right, so it's just a consequence of these basic axioms of your field. Okay. This actually was something that confused mathematicians at one point, right? Why does -1 times -1, why is a negative number times a negative number equal a positive number, right? Well, why is -1 times -1 equal to 1, right? But if you think about it axiomatically, then the answer is, if you assume, if you want your numbers to satisfy these basic properties, then -1 times -1 has to be 1. Okay, so it's a consequence. Okay. Everybody all right? You should be a little bit. How should you feel? Disgusted. Disgusted. Like, is this what we're gonna do? Yeah. Okay, don't worry. It won't last much longer. It will get. Okay. Okay, so other basic properties. Multiplicative properties. So first is that, given anybody in your field, then 0x has to be equal to 0. If x is non-zero and y is non-zero, then xy also had better be non-zero. So there's no zero divisors, right? No zero divisors. Okay. Part C, negative x times y equals negative xy equals x times negative y. And number 4, negative x times negative y equals xy. Okay. Good. you all look kind of bored and disgusted, which is about right. Okay. Okay, so let me just, I'm gonna sketch a couple of these, and then I'm just gonna go to the next topic. Okay, so you want to show that 0 times anything is going to be 0. Okay, you say, okay, well, consider 0 times that number and 0 times that number again. So consider 2 copies of it. Some of you may have seen this before in your linear algebra class. Well, then by distributivity, so this is going to be 0 plus 0 times x, right? Using the fourth property of addition. This is going to be 0x, right? And then by the previous proposition, number 2, right? This tells us that, so from B, from the cancellation proposition, that tells us that, this plus this is equal to this, so that tells us that, one of these guys must be 0. Okay. Number 2, we'll do by contradiction, right? To show that whenever you have 2 non-zero guys, their product has to be non-zero. So suppose, so do by contradiction. Say that x is non-zero and y is non-zero, but the product equals 0. We know that since each of these guys is non-zero, they all have multiplicative inverses. They both have multiplicative inverses. So then you say, well, if you multiply by the multiplicative inverses, right, that's also going to be 0. Right? Because on the right-hand side, of course, we get 1 over y plus 1 over x times 0. We'd associate, use base things, and that would be 0. Okay, and then, again, associating properly, right? We would say we would get 1 here, and then use the multiplicative identity, and we would get this. That this was equal to 0, but that tells, again, using the multiplicative identity, that tells us that 1 would be equal to 0. But that's not good because we said 1 can't be equal to 0. Okay, so that would be a contradiction. And so on and so forth. Okay, so you see how this sort of argument goes, right? You're trying to prove this sort of thing, and you're restricted to the axioms and some very elementary consequences of the axioms. Okay, so often I hear that sometimes in math camps they give these sorts of things as your first examples of proofs. I think that's a horrible thing to do, but I guess that's what they do. Yeah, I mean, these are very simple proofs, and so maybe it's a good example, right? You've got a very closed system. You've got 11 rules, right? What can you deduce from those 11 rules? 4 of them. Okay. Okay. Will we escape this before the end of the class? I hope so. So, Okay. Okay, a couple more definitions. Ordered field, right? We've talked about ordered sets, and we've also talked about fields. It's not the case that a field is just a. I'm sorry. It's not the case that an ordered field is a field with an order, right? It's actually a field with an order, and the order has to interact with the multiplication and addition in a good way. Okay, so it's more than just a field with an order. So let F be a field, and this thing an order on the field. Okay, so if whenever y is less than z, we have that x plus y is less than x plus z, right, for all x in the field. So addition, adding something onto both sides doesn't change, preserves the order. Okay? Adding something onto both sides preserves the order. And two, whenever x and y are bigger than that, additive identity guy, then the product is still bigger than that additive identity guy. Then we call the field with this ordering an ordered field. Okay, so Q with the standard ordering is an ordered field. Do you have a question, Fernando?
Yeah, so I'm wondering if there's any counterexample that violates these rules.
Yes, actually.
Especially for rule 1.
Yeah. Well, so you will see in your homework actually that that it's impossible to make C into an ordered field. That'll be one of your homework problems. Okay. So, yeah. So that was what I was going to ask next. In fact, I'll just state it. C cannot be made into an ordered field. And then there's a bunch of properties that follow from this, and I'm just going to state them. Whenever you have an ordered field, so if F is an ordered field, then a bunch of things happen that you expect to happen. If x is less than 0, then negative x is bigger than 0. If x is bigger than 0 and y is less than z, then xy is less than xz. If x is less than 0 and y is less than z, then xy is bigger than xz. If x is non-zero, then x times x, right, x squared, is always bigger than 0. And the last one is x and y, x is less than y and they're both positive, then they're still positive, and 1 over x is less than 1 over, is bigger than 1 over y. So whenever you have an ordered field, these things that you're familiar with actually do have still hold. Okay, and we'll use them shortly. Okay. I'm not gonna prove them for obvious reasons. Let me ask just one question. Suppose you take the integers and you mod them by some number, so nz. Do you know what I mean by this? Right. Okay, I hope you do. Is that a field? So like if I say z mod 3z, what I mean is that you'd have only the numbers 0, 1, and 2, and that the way you add these guys, if I take 2 plus 2, then I'd come back to 1. You'd sort of go in a loop and you come back to 1. 2 plus 1 would be 0. 1 plus 2 would be 0. 2 times 2 would be 1, right? Because I would get 4, but mod 3 would be 1, right? And so on and so forth. Okay. Is that going to be if I take z mod some number and then use the standard addition and multiplication on it, would that be a field?
Not necessarily.
Not necessarily. Who said that? Oh, yeah, Dave. Yeah, why not?
Because it has to be the prime number that you mod.
Yeah. It turns out that if it's a prime, let's see what happens if it's not a prime number. Suppose you have z mod 4z. Why is that not a field? Why is that not a field? Do you have any problem with the addition? Well, everybody has an additive inverse, right? 1 plus 3 is 0, 2 plus 2 is 0, 3 plus 1 is 0, blah, blah, blah. That seems okay. Yeah.
If you do 2 times 2, then you also get 0.
Yeah. Okay. So that's trouble, right? 2 times 2 is 0, and we said that whenever you have a field, you have no 0 divisors, right? But that would say that 2 is a 0 divisor, right? And so that this can't be a field, because it fails that property. Okay. So just to give you an example of maybe something you haven't thought about. Okay. Not much time. I was hoping to get much farther than this. Okay. So we're just going to put this on as a theorem. There is an ordered field that one contains the rationals as a subfield. So that is to say that that Q is a subset of that field, and the multiplication and addition on the containing field are the same. Agree with Q's multiplication and addition. And 2, it has the least upper bound property. So there actually is an ordered field that has the least upper bound property, and it contains Q. We call this field R. Okay. It's possible to you can construct a field using a method called the method of Dedekind cuts. I should say one can construct an ordered field that contains Q as a subfield and has the least upper bound property. This guy's called R. Okay, and you seems like some of you have read the construction in the appendix. I was going to say that we're not going to look at that appendix because it's quite intricate. I don't think you want to look at it at this point. There's a method that you can use to construct it, and you construct the field R in this way. So that's okay. Now this field R is going to have certain properties. Properties R. The first is called the Archimedean property. That whenever you have any real number that's positive and any other real number, then there exists a natural number such that nx is bigger than y. Okay, the Archimedean property. Given a positive real number and some other real number, then some multiple of that positive real number is bigger than that other number. Okay. I was looking through my old college notes when I took this course, and it said something like the spoon and the bathtub, right? In other words, you have this bathtub and you have the spoon. Eventually, you're going to empty the bathtub with the spoon, right? Right? There's going to be some number of times you use the spoon that will exceed the volume of the bathtub. Okay. Does anyone remember how this goes? How the argument goes for this? Does anyone remember? The proof is by contradiction. Okay, so proof by contradiction. Okay, so suppose that it's not the case, right? No matter how many times you use that spoon, you never empty the bathtub. Okay, so in other words, if we look at the set nx, where n ranges over all natural numbers, suppose that this is actually, right, suppose that nx is actually less than or equal to y for all natural numbers. Okay. In other words, this set nx, where n ranges over all natural numbers, is bounded above by y. Okay, what are we going to do? What's the obvious move, or what's maybe the only move that we can make at this point? Right, this is a statement about R. Right. What's good about R?
It's the least upper bound.
Is the least upper bound property, right? So this is bounded above, so it has the least upper bound, right? So this set has the least upper bound. Call it let M be that least upper bound, denoted by M. Okay. So now comes the sort of clever part. Consider m minus x. Right? Consider m minus x, where x is the size of the spoon. X is the spoon. Okay. This guy is the least upper bound, right? So we know that this is not an upper bound, right? it is not an upper bound of the set. Are we calling the set anything? Yeah, let's call this, I call this set A in the notes. It's not an upper bound of A. So it's not an upper bound of A. So that means that m minus x is less than or equal to some element of A. Right? Okay, so far so good, right? It's not an upper bound of A, so that means that m minus x must be less than or equal to somebody. There's somebody in A who is bigger than or equal to this guy, right? Because it's not an upper bound. Okay, but now, does anyone remember the end, the punchline of this sort of humorous proof? Then see that m.
Add x to both sides.
Yeah, add x to both sides. Great. M is less than n naught plus 1x. Right? But m was supposed to be an upper bound of the set of all multiples of x. M was supposed to be an upper bound to the set of all multiples of x, but here we found a multiple of x that is bigger than m. Okay, so that's a contradiction, right? M, remember, m was an upper bound of this set, right? And now we're saying that m is not an upper bound of the set, so contradiction. Okay. Okay, I think we will stop there because I don't probably don't have time to finish up the density property. Okay, so we'll stop here for today, and we'll go on next time.